All right, let's go ahead and get started with today's discussion section. First off, are there any questions related to midterm logistics or what's going to happen next? All right, so the TAs are going to finish grading. They're about halfway done right now. By the end of the day, we should have them fully graded. They'll be up on Gradescope and you can see how you did. I'll also post statistics of how the entire class did, just so you have some idea of your performance relative to everyone else. Midterm regrade requests are due within 1 week. And I will caution you that we will regrade the entire exam to look for any other inconsistencies. So make sure that your request has merit and that it's not just you want half a point here or there. We are using Gradescope, and so the grading is very consistent across every exam. You know, the TAs have come up with rubrics, and so they're taking off points uniformly for everybody. So I normally don't like a lot of this remote teaching, but I will say that Gradescope is probably something that I will keep moving forward because I find it very useful for that. A few other notes from the TAs and the grader. One is that at this point, we are all engineers. And so if you wanted to write out, for example, 1 millivolt. How do you think a reasonable way for an engineer to write 1 millivolt? Well, what are some options? What could we do?
1 MV.
We'll go to what. Yeah. All right. So we could write 1 millivolt, right? And note that 1 MV, capital M, that's mega. So that's not the same as milli. What do you think the TAs and the graders are seeing a lot of, though, for millivolts?
Probably big M.
So we see a lot of this. And, you know, milli is not so bad, but what happens when we start writing nanovolts? So we have a whole bunch of zeros before all of the answers, right? Same thing with scientific notation, right? So, you know, physicists like 1 times 10 to the minus 3 volts, right? We have a whole lexicon of units that as engineers we use. And so we try to get things into kind of these formats. And so I would strongly encourage you, as you continue on through both this class and your career, to start using milli, micro, nano, pico, femto, kilo, mega, to describe all of your units and then put them in kind of these form factors. All right, there have also been some issues that the TAs have talked about where we spent a lot of time in the small signal model in particular and we spent a lot of time where we talked about things like 1 over GM. But remember that 1 over GM is a very special case. It happens when we have this connection, when we have the gate and the drain tied together. Okay? If we do not have this connection, then the impedance that we see looking in out here is not 1 over GM. So without this connection, it's not 1 over GM. What is the impedance that I see looking back into the circuit?
R0 into GM, whatever is on the source side, if source is not ground.
Yeah, so R0 is equal, or R out, big R out is equal to little r out, okay? Why is that? What am I doing with this VGS term?
grounding it.
Anytime we calculate the output impedance and we're looking back into the circuit, two-port network theory tells us that we have to turn off the input. And turning off the input, if I have a current source, means that I open it. For a voltage source, it means that I short it. And so that means that my input is ground, thus VGS is 0. And so I have no current that flows through this device. And so my output impedance is just RO. So don't always assume that the output impedance is 1 over GM or the input impedance is 1 over GM. 1 over GM is a very special case when we have that connection, okay? Or if we're looking up into the source of a common drain transistor. All right, any questions about calculating input output impedance?
So what I do is I never replace it with 1 by GM. I just write it as GM VDS and it itself comes out as 1 by GM. That should be okay, right? I still place it as GM VGS.
Yes, if we have this connection. If we don't have this connection, what I'm talking about is a lot of the students are automatically just saying that the impedance here would be 1 over GM, which it's not. The output impedance here is R naught because we don't have the gate and the drain connected. If we did have them connected, then yes, what you're talking about is right. VGS is equal to VDS. And then the output impedance is going to be 1 over GM in parallel with R naught. All right. Next comment that the TAs have made, and I've kind of seen this from the midterm questions as well on Piazza, there seems to be some struggle with drawing the small signal model. If you're having issues with this, I would get this resolved as quickly as possible. We're going to start to transition in this course in the last, call it month and a half, to much more complicated circuits. Long gone are going to be the circuits that have 1 or 2 transistors in them. The lecture this week already kind of starts to point towards what we're doing with circuits where we will throw lots of extra transistors to fix small problems, right? So if you're having problems with drawing the small signal model of a circuit, I would get good at practicing this. And if you need help, come to the office hours of either the TA or myself, and we can go over some more examples, but this is definitely not going to go away. It's going to be a persistent problem if you don't address this. Any questions about small signal model? All right. There was also a couple of questions that the TAs had relayed that related to Miller's theory, and in particular, that we have a capacitance in feedback. What do we do with this capacitance C when I want to create an equivalent circuit that has grounded impedances? I take C, I ground it at the input. I have my amplifier now in open loop, and I have another capacitance at the output that is also grounded. And these capacitances, of course, have changed in magnitude. Now they're Z1 and Z2. So it's very obvious what to do when I have this kind of with this amplifier drawn like this, but apparently there have been some issues where students had problems on the homework in particular, where let's say that the amplifier was implemented and look something like this. Okay, and so the cap that we're talking about that happens to be in feedback is CGD. When I draw the small signal model and I use Miller's theorem, where does CGD at the input and CGD at the output connect to? What nodes? Somebody help me out.
Wait, can you repeat the question?
So when I take CGD and I apply Miller's theorem, where does this impedance Z1 and Z2, what nodes does it connect if I implemented it with this circuit on the right?
One of them would be on the gate, the other one would be on ground.
Yeah, so one goes to gate to ground. And what about the other side?
Drain to ground.
Yeah. So there was some confusion. Apparently students were thinking that maybe it should connect down here to the source. But remember, the intent of Miller's theorem is to take this capacitance and create an equivalent impedance that's grounded at the input and grounded at the output. So it doesn't go to this intermediate node, it goes directly to ground. All right, and then last comment before I'll talk about a couple of things today. Please make sure that if you are having issues with any of the content in the class or have questions, that you use the rest of the resources that we have available, namely that you use Piazza and office hours. This week for the TA and myself, office hours were rather light. And so I hope that everybody did well on the midterm and that there was no questions or doubts. But I would encourage you to use the resources that you have available to you. All right, with that, we're getting to the part of the course, that's really big, where we're actually going to start to use the skills that you've learned, and we're going to apply them to a real world project, okay? And so this is the design project that is now going to be posted after class today. You'll notice that it's not due for about a month. This gives you quite a bit of time to work on it, but I will caution you that this is a very time-consuming project. It's not something that you can finish in a weekend, and it's not something that you can finish even in a couple of days before the weekend. This is a month-long project, and so you should get started fairly soon. And started can mean a lot of different things, and I'll talk about that in just a second. So what we're going to do is you're going to redesign a sensor interface using a new technology. So in kind of terminology, this would mean that you're porting a design from one technology to another. So for example, let's say that you joined Apple and Apple was moving to the new 5 nanometer process. They may have a design for an amplifier that worked in 12 or in 14 nanometer, and they want to port or translate that down to 5 nanometer. So that's kind of your idea here. I'm giving you an architecture for this particular circuit, and what you are asked to do is to find all of the sizes in order to meet this specification table that we'll talk about right here. All right, so the spec table for our project, one, we're going to use the same technology that we've been using in class. We're not going to go into corners or into PVT, so we'll just use the nominal process corner. We're going to operate at room temperature, standard supply voltage of 1.8 volts. And our amplifier that I'll show you down here, it has to drive a 5 picofarad load. The input common mode range is 0.2 to 0.8 volts. I will talk about what this means in just a second. I have a few slides that I can go through. The output common mode voltage, this is just the DC voltage, has to be between 0.4 and 1.4 volts. Why do you think an amplifier would have these two specs?
Probably
So
keep
output
it
you
within
want
a certain. Probably keep it within a certain operating range.
Yeah, but what else?
You want higher swing on the output and not so much swing in the input?
Okay, so I mean, one reason, one of your colleagues suggests, well, the output, you kind of want this to be around VDD over 2, maybe. And the reason being that that gives you the maximum swing up and the maximum swing down. That's also possible, but it's really related in some sense, to the input common mode range, right? So recall that a differential pair, it can have an input DC common mode within this entire range, and it shouldn't affect the parameters that we care about, things like the gain, the bandwidth. Where this spec comes in is that this amplifier has to drive another amplifier. And so you would want the output common mode voltage of this amplifier to overlap with the input common mode range of a subsequent amplifier. And so often these two are quite linked. Your colleague's suggestion of putting the output right in the middle is typically a pretty good one if I have wide swing. Not always the best one though. All right, power dissipation. This is where we are always going to try to optimize. Oftentimes your objective is to meet all specs and then minimize something else. In this case, we're going to try to minimize the power consumption of this amplifier. And I've given you a reasonable starting point of about 2.5 milliwatts. The specs are different, so I can't say exactly, but I will say that in the past, students will do 10x better than this, 50x better than this number. This is really kind of where it gets to be a little bit fun, is that it's somewhat of a class competition to see how each of you can do given this large design space that we'll have here. Then we have a spec on the small signal gain, the DC gain, as well as the bandwidth, a phase margin spec, gain margin spec, and then a couple of other things that are we're imposing just based on where we design. That's when we have current mirror M factors. And so that's to say that the ratio of currents from something like, well, here's a good one. This guy to this guy can't be more than 1 to 20 or 20 to 1 alternatively, okay? Again, we talked about the reason behind this being that we want good matching between the devices. And once we get beyond 20 to 1 or 1 to 20, it becomes very hard to have the devices match very well. And then the last constraint here is the gate overdrive voltage must be greater than 150 millivolts. This is to put the devices in moderate inversion such that we don't have to deal with quite so many short channel effects in this project. All right, so what are you supposed to do for this project? You have to find the sizes for every one of these devices in order to meet these specs. So very quickly, how many transistors do we have here? 20-ish. And we have W's and we have L's for each of them. And we have VOVs for each of them. So there's a tremendous amount of design space that we have here, which basically should be that there's going to be no two designs that are exactly the same. And so the way that I showed kind of this optimization previously, what we're trying to do here is get you to work through first getting a working design, and then work on how you would optimize the design and show your chops that you really know how to do this. All right, you can work on this project alone if you'd like, or in teams of 2. No more than 2 though. So if you have somebody that you've been working with or have good rapport with, I think that that's a reasonable thing to work with them. If you're looking for somebody and don't currently have a partner, we can set up something on Piazza to facilitate team making. But keep in mind that you guys are tying yourselves to your partner. This is a lot of work, and so I would strongly suggest that you have a partner if you feel comfortable. You will each submit one report, and I'll talk about the report in just a second. You can talk about the design with other teams, but your design must be unique. Again, this comes back to the fact that there are 20+ transistors in the circuit, each of them having 3 design variables. There's going to be a very large design space. Nobody is going to have the same design. And under no circumstances should you exchange your design or give your design files to another team. Okay. All right, who thinks that they could do this circuit this weekend?
Definitely no.
No? Who thinks they recognize parts of this circuit?
I have a question about the circuit.
Yeah.
So the current bias, doesn't it require a startup circuit to the far left?
Good question. It could. Our reference circuit over here may require a startup circuit. Due to its arrangement, it probably won't though. If your design does need one, you can add a startup circuit. All right, so let's just quickly look at this though. Let's break this down into pieces because that's what engineers are good at. We're good at compartmentalizing things. What is this? We've seen this.
Current.
Yeah, this is a
Is current.
this is a constant GM. Right? What is this?
Yes.
Or I guess more appropriately, what is this?
Differential amplifier.
Yeah, this is a differential pair. All right, what is this?
Cascode.
Inverter.
Close. This is a common source. All right. There are a few things that we probably don't recognize. This one, we can see that there is some cascoding. And over on this side is a whole bunch of bias circuit that's used to bias the various different nodes that we'll have to sit down and analyze. Somebody commented, is it breaking up for everybody?
Not for me.
It's fine for me.
Okay. All right. Sorry if you have bad internet connection. I just wanted to make sure it wasn't my internet connection. All right. So all of this is a bunch of bias circuit that you guys are going to have to analyze and kind of sit down and think through. We'll talk about this very soon. And we'll talk about this part very soon as well. This is what's known as the compensation circuit. So this is to position the poles and the zeros where we want them and shift around the frequency response. Okay. All right, so I'll say this again, this project is, it's just a lot of time and effort to make good design choices. You have to analyze the circuit, you have to understand the trade-offs, you have to set up the simulations, and then you have to document your work and explain to us why you made those choices. So my recommendation here is do not wait to get started. There are definitely parts of the circuit that even today you could get started on. For the next, I don't know, 4 or 5 weeks, there's a little bit less homework in the class. We're going from homework being due once a week to once every other week. And so the idea being that this should give you time to work on this now. And we have a whole week without class. So there's a good amount of time to spend working on the project. I will comment that in the past, the lab projects or the lab computers have had issues towards the end of the quarter, especially since a lot of the ECE courses have projects this quarter as well. Try not to wait until the very last minute because these issues will definitely come up and they're very hard to deal with if it's the day that the assignment is due or an hour before the assignment is due. You essentially have a month. You should use this effectively and not wait until the very, very last minute. Okay, so what do I suggest in terms of a design flow? Well, if you look at this circuit, I would assume that a lot of you would say that this is overwhelming, that there's a lot going on here and you may not even know where to start. Okay. the first thing that I would do is I would study this entire project and find a partner. Okay. And as I said earlier, if you need a partner, we'll facilitate that with Piazza. The second is that you should look at figure 1 and think about how all of the different blocks interact. And we should draw simplified versions of them. Okay. When I say simplified versions, what do I mean? We know that this is generating a bias current. So I would rip out this whole chunk of the circuit and replace it with a bias current. I would similarly put in a whole bunch of ideal current sources here rather than using these current mirrors. I would simplify this and start with one stage of this amplifier, i.e. take off the whole second stage. And then I would look at the second stage after I got the first stage working. So when it starts off, you're going to be simulating very, very simple circuits and lots of ideal current sources in there. And then you can start to add back in complexity as you go along. Okay. The important thing to do early on, though, is to figure out what knobs you have to turn. And you're going to do this by analyzing the circuit, as we've done many times, and then verifying your analysis through simulation to find out knobs. And when I say knobs, really what I mean is, what affects the DC gain? You need to have an expression for the small signal gain. You need to know what the small signal bandwidth is. You need to know where the poles are because we have to calculate the phase margin. You need to know where the 0 dB frequency is, or the unity gain frequency, in order to calculate the gain margin. We have to be able to calculate all of the currents so that you can calculate the power. So there's a whole bunch of calculations that we need to do and equations that we need to derive in order to understand what the key components are that affect the performance here. After you get this working, then I would set up a script like I've done in the past to kind of show you ways of iterating. So the idea is not that we wildly sweep W's and sweep L's and try to find something that works, because with this many design variables, the chances of you finding a working design just by sweeping, even if you started today and ran it for an entire month, are pretty slim to none. Okay, you are going to have to do some calculations, and then you may want to iterate around those calculations or look at optimizing and look at the trade-offs. And that's where having the script, I feel, is very useful. This can be in MATLAB, it can be in Excel, it can be in MathCAD. The whole idea here is that you can change a few variables and iterate on your design without having to go back in and hit SPICE and simulate the entire time. It's much, much, much faster for MATLAB to calculate all of these things than to go run a simulation. Okay, you'll use the simulation to verify your results, and you need to identify any kind of discrepancies. Okay, and so that's what I mean here is that we're going to simulate in SPICE, and you're going to come back and you're going to compare the results to your hand calculation. Do the currents match? Do the GMs match? Does the DC gain match? Anything that doesn't match, call matching 10% for hand calculation, you need to go back in and figure out what's wrong. And so track down these discrepancies. If your circuit doesn't work, look at things like, what's the operating point? Is it where you expected it to be? I can't stress this enough that we have to get a working design. And I will say that in the past, almost everybody over the course of nearly 10 years of teaching this course has been able to get this to work. Okay. It does take quite a bit of time to get it to work, though. All right, and then the last comment here, you have to write a report. You have to communicate to us what you did, and I would suggest starting this several days before the deadline. Your grade will depend partially on how good your design is, i.e. the power consumption, but more importantly, that you understand the design and that you can explain and document all of the various different aspects of this. I've had many students in the past take their report that they wrote for this class and show their Qualcomm hiring manager or show their analog devices hiring manager their report, just to show them that they know how to do this and they know how to document this kind of work. You know, I even recall back when I was in graduate school, I did very similar types of projects, and I even used them to get my internship at the time. So spend some time on the report, make it look nice, you know, do a good job writing up your results. A couple of hints. One is that what I mentioned earlier, your first simulation should not have all of the transistors that are in the figure 1. You should take out a whole bunch of them and use idealized current sources for biasing, many other things. You know, simplify things as much as possible and then add in the bias network. So normally when you design this type of circuit, you'll design the signal path first, i.e. this amplifier, this core amplifier, and then the second amplifier here, the second stage. Then you'll do the biasing. And at some point you have to come back in and do the frequency response. Okay, one other comment that sometimes is helpful is that when you are designing, for example, this stage, if you design this stage and you don't account for this capacitor here, CC or M9, even if you don't know exactly what they are, if you put in some estimate, what can happen is that you can not have enough margin in your design where when you do add these components in, they add too much load or too much capacitance to the circuit such that your design no longer has any chance of working. And so this is where it can be a little bit iterative in going back to designing and then kind of estimating what these parasitics are. But usually it's a good idea that as you go along, think about what's going to hang off of that node. And if there is something that's critical, i.e. high impedance nodes, add some capacitance of what you expect. This allows you to kind of hone in a little bit on the design space and not iterate quite so much. All right. And then lastly, your project report. So this will be submitted on Canvas. We'll run it through, turn it in to make sure that the reports are unique and that we're not having plagiarism issues. And your project report has to follow this template exactly. Okay? No deviations from this. Page 0, this is exactly what I want and only what I want. Page 1, this. This is kind of a free-form page where you can describe your design. How did you approach the problem? What were your key design choices? Pages 2 and 3, I want to see a schematic of the final design. Importantly, you know, I've given you an extra page this year. In the past, I only had 1 page. I'm giving 2 pages. I would suggest separating your bias current or your bias block and your signal path, i.e. cut the circuit in half right here. Put this on 1 page, this on the other page, and make sure that you clearly annotate things like the size, the resistance, the voltage, and the bias currents, okay? There is something posted in the CAD section of the wiki of how to change the annotations. This can be quite useful to get things annotated on the design that you want. Pages 4 through 7, this is where you're going to show us calculations. Okay. You know, this is probably the most important part of your report to communicate to us that you know how to do this. But I want this to be a synthesized logical flow rather than a brain dump. I don't want KCL, KVL at every single node in the circuit and just, you know, 7 pages worth of equations here. I want you to show me the key design equations as well as their values and why you chose them, okay? I also would like you to compare these with your hand calculations and the SPICE values in a table and show those discrepancies. So for example, if we designed this differential pair here to have a GM of 250 microsiemens, and our hand calculation showed 250, but when we simulated it, we only got 200. I want you to explain why. Explain to me what's going on that's causing that. You know, small discrepancies, call it 10, 15%. We don't necessarily need to fix, okay, unless they're affecting your performance. Things that are off by 50%, something is wrong, okay? Our hand calculations should not be 50% off. You need to hunt those down and either fix your hand calculation or look at your simulation. Something is going on, okay? Things that are off 50, 100%, those are significant discrepancies, okay? You need to show me your power dissipation, both simulated and calculated. And I will point out that in the past, you know, students have spent 99.9% of their time striving to get the absolute lowest power, okay? And this came at the expense of their report or their methodology, that essentially they couldn't explain how they got the lowest power, but they got the lowest power. That will not automatically get you the best score in this report. Okay. The project is one for you to learn how to do this and explain how to do this. I'm far more concerned that you can explain your methodology and that you have a good, robust design rather than you get the absolute lowest power. That said, I do like to encourage you to spend some extra time and to kind of make this project approachable for the wide variety of students that we have in this class. And so I think that that's where the competition aspect does come in, is that it gives people of varying different capabilities something to strive for. So the students that are really comfortable with this, you know, they can spend their time optimizing and getting it to work. Not everybody will have the lowest power. The power will vary dramatically. I'll show you a plot at the end of the power consumption of the entire class. You'll see there will be powers that are, you know, probably, if I was to wager a guess right now, 50-ish microwatts all the way up to, you know, 50 milliwatts. So 3 orders of magnitude of varying different powers. Okay. And then the last couple of pages here, 8, 9, these are to demonstrate to us that your design works. So you need to show us some simulation results and annotate things like the gain, the bandwidth, and the phase margin, as well as your hand calculations on that same plot. Last page is just for comments and conclusion. You know, talk about any issues that you had, things that you learned or maybe didn't learn from the project. And if you want to, you know, how you might improve the architecture in the future. So if you were given the flexibility to add or remove transistors, you know, what might you do to meet these same specs? All right, so this year we are going to have a submission script that you will use to submit your design. I will talk a little bit more about that later on. I probably will not have time to do that today. I have very generously provided a symbol for the project and a test bench. You can find these on the server in this directory. In order for the submission script to work, you have to use this symbol, okay? So don't change the symbol when you're doing this. Okay? All right, and lastly, in terms of grading, design flow, insight, optimization strategy, you can see this is half the points. So a good portion of your project is really just, can you explain what you did? You know, what was your design flow? Did you get insight from this? Write-up is 10%. Meeting the specs is 20%, and then 20% will kind of linearly rank all of the power consumption in the class and reward people that got the lowest power consumption. All right, so this is going to be available right after class today. Are there any questions about the project?
So, Professor, each group have one report or two?
Just one.
Okay.
Yeah, I may need to have you guys upload it twice on Canvas. I don't entirely know how to do that yet, but I'll let you know when I figure that out. Other questions?
So when you mentioned for the design flow, you said start off with the amplifier design, then the second stage of the amplifier, then maybe the bias, and finally the frequency response. So how do you start off with the design of the amplifier when you're not much concerned about the frequency? I mean, how do you do
No,
stage-wise amplifier that too?
yeah, you're absolutely going to be concerned with the frequency. Yeah, you have to, I mean, the frequency planning is probably one of the very first things that you have to do in this type of project. You know, where are you going to put your poles? Where are you going to put your zeros? Because that directly feeds into your unity gain bandwidth and your phase margin. And the majority of your power that you're going to spend is to get this phase margin.
Okay.
I'll talk a little bit more about the compensation and you know, some of these blocks in subsequent lectures, but I want to get this out to you guys as soon as possible so you can start with some of the aspects of it.
So if you can you name the remaining blocks? You named 3 of the blocks, right? Can you name the remaining blocks that you're yet to discuss?
Yeah, so I'm going to discuss OTAs. So we'll talk all about you know, amplifier structures. We'll talk exactly about this structure here. I will spend probably a discussion section talking about compensation, which is this aspect of it. This part, though, you have seen everything and I won't talk any more about it. We've seen this part as well. So really the kind of missing pieces that we have are just right here. And even this, we've seen part of it, but I'll do a little bit more formal job explaining it.
Okay, thanks.
All right, any other questions about the project today? All right, any questions about the lecture on differential pairs? All right, then I'm going to spend the last few minutes that I have talking about how you would simulate these types of amplifiers.
I have a doubt on your earlier lecture. Can I ask that? Just a little earlier on the.
How about we wait until afterwards or office hours now?
Sure. Yes, that's better. That's fine.
Sorry. All right, so given that we're going to have to do some simulation, I wanted to talk in particular about how you would simulate differential amplifiers. So from the differential amplifiers, recall that we need a differential input. That is, I need 2 inputs. And if I wanted to build what's called a balanced input, where I have the same, balanced input simply means that I have a fully differential input where the inputs can be written using this type of structure where I have a common mode that is unique, that is the same on both sides. And then I equally split the differential mode between both halves. Okay, so that's what's called a balanced input. And so what we've done here is I've created these 3 voltage sources to do this. And if you look very carefully, you'll see that I set the voltage of this one, the DC voltage, to be minus VDM divided by 2. This one is positive VDM divided by 2. And the DC voltage of this one down here, this is the common mode. Okay? And so the DC voltage of these 2 sources is equal to common mode minus VDM over 2 and common mode plus VDM over 2. So this is the input minus, input plus. Okay? Additionally, I've also set the AC simulation parameters. For the differential mode, it's minus ADM divided by 2 and ADM divided by 2. So if you think about a amplifier, why do we choose the AC amplitude to be 1? So if I had an amplifier and I wanted to run an AC simulation, almost always I don't know what you do, will set this amplitude equal to 1. Why do I do that? Because after I run the simulation, I just probe the output voltage And since my input is 1, V out divided by V in is V out divided by 1. That is the gain. Okay? So I don't have to divide by the gain of the input. In order to do this in a differential amplifier, that means that I have to divide and apply half of the signal to each of the half circuits. And so that's why here I'm getting ADM over 2 such that I apply half to the positive and half to the negative. The negative sign is because they're 180 degrees out of phase. All right, and then down here, I'm also setting the common mode or the AC gain of the bottom source down here equal to ACM. Okay? And so what I'm going to do, and I'll talk a little bit more on the next slide, this will become clear, is I'm going to use my test bench. And if I set ADM is equal to 1, that means that I'm going to be simulating the differential mode. That is that I'm applying a differential signal between in plus and in minus. On the other hand, if I set ACM equal to 1, then I'm applying the same signal to in minus and in plus, and I'm simulating the common mode. Okay? Importantly, I should not set both ACM and ADM to 1 at the same time. It's either or. I should pick and simulate the differential mode, or I should simulate the common mode. And then lastly, if we wanted to add source impedance, we could add a little bit of impedance to each side of this. We're essentially constructing a Thevenin model of what the previous amplifier would look like in this case. All right, any questions on our input source? All right, so here's my test bench. So my test bench that I'm showing you here, this is an open loop test bench. And let me walk through the various different components that I have in this test bench. By the way, this is exactly the test bench that I'm giving you for the project. So let's start off on the left side. This is the DC supply. This is VDD. So I'm giving 1.8 volts, and I've given this a name of VDD. This is the input source that I just described on the previous slide. This is what we'll call the device under test, or the DUT. This is the amplifier that I'm simulating. This is the load capacitance, or the load that I'm adding to this device. And this is in order to set the DC output voltage if I wanted to simulate the output common mode range. So I'll talk about this later on. We don't need to spend much time right now on that. All right, so you'll note that what I've done is I've set up all of these things in one test bench so that I can simulate everything essentially just using this test bench. All right, so here's how I set up ADE. I have these variables that were described on the previous slide. This is if I want to simulate common mode gain, differential mode gain, input common mode voltage, the differential mode voltage if I wanted to run, for example, a transient simulation. This is an AC simulation where I'm simulating from 1 to 10 gigahertz, and I'm running a DC simulation in order to get the operating point as well as the power. Okay? And then I've set up a whole bunch of outputs to measure things of the performance essentially of this amplifier. And I'll talk about each of these on the next slide. All right, so what do I want to measure? Well, one of them is the 3 dB bandwidth. And the way that I do that is I look at the AC simulation, so that's VF, of the output node, and I look at the 3 dB low pass bandwidth. I can also measure the gain bandwidth product. So this is, again, the output frequency and the function that Cadence has built in is called gain bandwidth product to do that. And so you can see that there's a whole bunch of these that I've set up, and I just put them here so that you can all see them. They're all in the test bench that you will get as well, so you don't need to understand these. But essentially what this does is this allows us to calculate each of these various different components that we care about. Okay, so the Cadence has built-in functions for a lot of these. It even has many, many more that I'm not talking about. If you want to see a list, you can use the calculator. I will point out a couple of them that are, I guess, more complicated. So this one here, this is the DC voltage gain. And so what I'm doing with these functions is I'm grabbing the magnitude response of the output, and then I'm taking the value at DC or at 0 hertz, and then I'm converting that to dB20. So this is the gain, the DC gain in decibels. And then lastly, down here, the power, I'm calculating I'm finding the DC current of that supply voltage that I talked about on the previous slide, V3. And then I'm multiplying it by the DC voltage of VDD. And the current notation that I did, I took the positive current, so I'm multiplying it by -1 to get a total power consumption. All right, so what these do are these let me calculate all of the metrics for the project when I run my simulation. So I don't have to go look at the Bode plot and try to find the -3 dB frequency. I simply look at this output and I know the 3 dB frequency. Similarly, the gain margin, I don't have to go eyeball it from the Bode plot. I just look at the gain margin output. All right, so let's look at a couple of the simulation outputs. This is the DC operating point, and so you can see that I'm showing all of the currents. My amplifier here is taking 10 microamps. I've put a 500 millivolt input common mode with no differential mode, so both of the inputs are 500 millivolts. My output, I've set it to 900 millivolts with this output source. There's some current that's flowing back into the amplifier, and I'm loading this with this cap. More importantly to you than the values out here is probably what's going on inside. Okay, my amplifier is a model, and so it's not really a transistor level amplifier. It's a macro model that lets me simulate all of this. So the internals of my amplifier are pretty boring, not nearly as interesting as yours will be. All right, so now if I wanted to do the differential mode gain, my setup would be that ADM is equal to 1. The common mode ACM, this is again, the common mode gain is equal to 0. I still have to put an input common mode voltage that is within my input common mode range. And then the output I'm just setting to mid-rail right now, 900 millivolts. Okay. And so from the AC simulation that I'm showing here, where I have gain and phase, I can pick off all of these parameters. I can find the DC gain, the 3 dB bandwidth, unity gain bandwidth, phase margin, gain margin, as well as the gain bandwidth product. You'll also remember that I'm running a DC simulation, and so this gives me the DC operating point as well as the power that my circuit is consuming. If I wanted to simulate the common mode gain, I would change ADM to 0, set ACM to 1, okay? And then I could again find all of these parameters, and then I'm showing the result over here. The caveat being that my amplifier is ideal, and so it has common mode gain of 0. And so anytime you're talking about -5 kilodB, it's quantization error in numeric results. I mean, this is as close to 0 as you can possibly get. Yours will probably be much more interesting in that regard. So the input common mode range. I'll talk a little bit more in a subsequent lecture, but I wanted to at least kind of put this on your radar right now. Really, when we're talking about the input common mode range, what we're trying to do is find a DC input, a VCM that I'm going to apply to this differential pair that keeps M1 and M2 in saturation. Okay? And just as a quick thought experiment, what would happen to this particular circuit if I took VCM or both of these inputs and I started pulling them up? What's going to happen to M1 and M2? Well, how much current flows through M1 and M2?
I tail over 2.
Yeah, so if there's no differential mode voltage, both sides are going to have the same current. They're essentially going to split this. And so what voltage, what DC voltage is this? This is VDD minus I tail over 2 times R. Okay. And so what happens to the drain of M1 when I keep raising VCM up and up and up? The source node goes up with it. The drain node, it's stuck. The drain node can't move. It's always this voltage. So what happens to M1 and M2 when I keep increasing the common mode?
They come out of saturation.
They go into triode essentially, right? And this whole circuit is really predicated on getting good transconductance, or GM, from M1 and M2. And we know that once you enter triode, we no longer have good transconductance. And so the gain, GM times R, of this differential pair would start to fall off pretty dramatically if the common mode was outside of the range. Same thing if I was to take the common mode down. You know, I'm showing this as an ideal current source. More realistically, we would probably implement this with a transistor. I would essentially get to the point where I started squeezing the drain voltage of this tail source, and I would take the tail node out of saturation. Okay? So this is what defines the input common mode range for this amplifier. Now, when we're actually simulating or you're measuring on a bench, it's very hard to kind of correlate these two. When I'm simulating, I can simply look at the operating point and I can tell if M1 and M2 are in saturation. When I'm measuring this on the bench, I don't know what region any of the devices are in. The only thing I know is the output. And so oftentimes you will define the common mode input range using the DC gain. Okay, and so you'll get a curve that looks like an inverted bathtub, and we'll define bounds on how much DC gain we're willing to lose due to the input common mode range. All right, so how would we simulate this in our test bench? We would set the differential mode gain to 1, common mode gain to 0. The input common mode voltage, we would do a parametric sweep from 0 to VDD, and I've shown that down here. And then we would look at the DC gain. So I've thrown away all of the other parameters. I'm only looking at the DC gain. And normally you would see something that looked a little bit more like this, kind of this inverted bathtub. Again, since I'm using an ideal amplifier, mine doesn't have an input dependent gain. Okay. Usually you'll define the input common mode range where the gain falls off by about 3 dB from its maximum. And so that would be, you know, this range that I've shown here in blue. All right, the exact same thing is true for the output voltage range as well, where I want to know what range keeps all of these, output voltage range keeps all of these in saturation. Okay. And again, same kind of caveat as before. It's easy to do in simulation, harder to do on the bench. And so we'll use the DC gain as our proxy. It can be different ways. Feedback that we're going to look at later on in the next few weeks, they will not have this. And I'll give you one example, is that if this resistor was instead replaced by a transistor, this voltage here could take a whole bunch of values and still keep these two transistors in saturation. And that's the case where we need to set the output voltage and look at how much we can push it around. Your project also has this exact same thing, where the output stage is a common source amplifier, but it's loaded with an active PMOS device. And so the DC output voltage is not well defined. And so we would need to do something like this in our test bench as well. So how do we do this? How do we set the output voltage? The input is rather easy because if you look at our test bench, you know, we're defining it. We set the input common mode. The output common mode, we need to use this other structure that I was showing you earlier here, where we have another voltage source that sets the output. But importantly, I have to get this out of the simulation. What would happen if I left this voltage source here and I just directly connected it to the output? And then I run an AC simulation. What am I going to get for the gain?
0.
Yep, I'm going to get 0. Why? What's the simulator going to do when it starts up and it wants to do a linear equivalent of the circuit?
Output will be forced by the V out.
It's going to do the
Maybe
same
for-
thing we do when we do small signal analysis. We take independent voltage sources and we short them. And so in that case, the output would literally be shorted to ground. So we could wiggle the input all we wanted and the output would do nothing. Okay? And so what we've done is I've used this switch. Okay, and this switch lets me set the initial condition. So these are switches in the analog library. This one is called SP1T switch. And the interesting thing is that it has all of these different parameters here. So if I just want to set the switch position, that's this top parameter. So I can either set it to open or closed. But more importantly and interestingly, when I have DC, AC, transient, and initial condition, what this lets me do is it lets me set the DC position of this switch to 1, i.e. close it, and for the initial conditions, close it. But when I'm running an AC simulation, I get this DC voltage source out of the circuit. Same thing if I wanted to do a transient. I don't want that DC voltage at the output, so I would get it out of the circuit. So this is another way of setting kind of the initial condition of this node. You can also do it with .IC and force. There's a handful of different ways of doing it. I think this one is the most elegant and most obvious to people what you're trying to do. All right, so how do we simulate the output common mode range? Very similar to the input common mode range. Now we're going to set the input to a range, a voltage that's within the input common mode, and then we're going to sweep the output voltage from 0 to VDD. Okay, and so that's my second line in my parametric sweep down here. You'll notice that you can set up a whole bunch of different sweeps and just not turn them on by not checking them here. And so here I'm sweeping the output from 0 to 1.8, and I'm doing 18 steps of that. It's shown up here where I'm plotting the DC gain by the output voltage. Again, my model is very simple. It doesn't, the gain essentially is independent of the output voltage. And so I see just kind of a flat 80 dB gain the entire way. Yours definitely will not do this. It will have this kind of inverted bathtub shape that looks something like this. Why is that? If I go back real quick, oh, I don't have your project open. Never mind. So the reason being that, you know, when I put a very low DC output voltage, if you think about your project had an NMOS common source with a PMOS current source. At very low voltage, I'm essentially turning off that NMOS. Same thing at very high voltage, I'm turning off that PMOS. And so I will lose a ton of gain from that circuit in both of those scenarios. There's some voltage that I need in order to keep that current source happy, both at the input and my amplifier, at the output on the low side as well as the high side. So that's why we'll get this inverted bathtub-like shape. All right, any questions about simulating amplifiers or projects at this point? Great. All right, well, have a great day.